Good morning, Dr. Long Yi. Here is Zou Yiming giving the presentation about fabrication of palladium thin films by ALD method. I'm a PhD student from MSE, and my supervisor is Every Talk. Here's the outline of my presentation. It includes 4 parts. In part 1, I will discuss why do we need to fabricate PD thin films by ALD. And in part 2, I will give the research stages. And in part 3, the possibility of using PDHFAC2 and an oxidation agent as a precursor will be discussed. And in part 4, I will show some discovery of my group. So let's get started with the first question. Why do we need palladium thin films? My project focuses on fabrication of high entropy alloying coating by ALD. High entropy alloying is the alloying consists of at least 5 different kinds of metals. And even though bulk high entropy alloying has been widely investigated, the research on thin film is rare. So our group is trying to fabricate high entropy alloying coating by ALD method. First, we need to fabricate thin films of single metal. And second, we need to fabricate the multi-layers of 5 different kinds of metals. In our project, we choose PT, PD, RU, IR, RH, 5 normal metals as the components. And third, we will get alloying of the multi-layers by spark plasma sintering method. And in our study, we use palladium thin films as the first layer because according to simulation results, palladium thin film can be also used as the seed layer for deposition of other metals. Here are 3 kinds of common precursor of PD, and their chemical structure are shown in the picture below. And so far, the precursor with reducing agent and oxidation agent following by reducing agent have been proved feasible. However, the precursor with only oxidation agent is invisible. And next, I will discuss these three different kinds of precursors one by one. The first precursor is PDKEIM22. This precursor is used with oxygen. The temperature ranged from 250 to 275. Even though in this study, PD thin film was finally fabricated. However, the film growth rate did not saturate to a constant level when the precursor pulse time was increased. Let's look at the picture on the left side. This is a typical relationship between pulse time and the growth rate. As we know in the class, during ALD process, reaction can only happen on the surface because the area of surface is limited, so reaction is also limited. And if the surface is fully occupied by the precursor, the reaction will stop. So there must be a maximum point. And beyond this point, the growth rate will not increase anymore. However, this point was not observed in this study. The second precursor is PDTHD2. The precursor is used with ozone. However, it only results in the thin films of palladium oxide. To solve this problem, hydrogen pulse was used after each ozone pulse to reduce palladium oxide to the pure palladium thin film. They finally succeed in fabricating a PD thin film with high purity. However, different from PDO films, the PD films were non-uniform across the substrates, as a large thickness gradient was found. So this precursor was examined with limited success. The third precursor is PDHFAC2. This is the most widely used precursor in PDALD. There are three processes in total. And for the first two processes, which use formalin and hydrogen as precursors, the fabrication was successful. However, the growth rate of palladium thin film was very slow at the beginning of the process. So then it was discovered that one of the byproducts, ALHFAC species, hamper the process. So where is the alumina come from? Actually, alumina is usually used as the substrate for PDALD. However, in this process, it also joins in the reactions. The reaction has been shown here. This reaction will form ALHFAC species. This species will always stay on the surface, occupying the space and preventing the attachment of precursors in the next step. So the process slows down. To solve this problem, in one study, oxygen plasma was used after the hydrogen pulse. This study resulted in uniform PD thin film with high purity, and the growth rates also increased. And according to the gas phase FTIR project, it was discovered that after oxygen plasma step, the intensity of carbon dioxide increased. So the study believed that the contamination of ALFAC species can be essentially attributed to the contamination of carbon. So far, people have already got a way to fabricate uniform PD thin film with high purity. Now here comes the last questions. Is it necessary to consider the possibility of using PDHFAC2 and an oxidation agent as the precursors? The answer is yes. There are two reasons. First, as we know in the previous study, an oxidation agent helps eliminate the contamination of carbon, so it can help increase the growth rate. And the second reason is the safety issues. As we know, hydrogen is highly explosive, so it is prevented by many institutions, including NTU. So we need to find another way with our hydrogen pulse to fabricate PD thin films. But it is also difficult to achieve because first, no one has ever succeeded in fabricating uniform PD thin films with an oxidation agent such as H2O2, water, oxygen, and ozone. And it was concluded by many other papers that the fluorine in the precursor is the reason of failures. Here I show the chemical structure of PDHFAC2 again. As we can see, there are many fluorine atoms in the molecules. However, there is no theory to explain how a fluorine atom affects the PDLD process. In the previous study, we can see after oxygen plasma step, not only the intensity of carbon dioxide increased, but also we can see the peak of carbon fluorine species disappeared. So this result implied that the fluorine might not be the reason for the failures. And in another study, researchers increased the temperature to study the thermal decomposition of PDHFAC2. They also discovered that the carbon fluorine species disappeared if they increase the temperature. So in fact, carbon fluorine species can be eliminated by increasing the temperature. So it is still possible to fabricate PD thin films with an oxidation agent. Here's our discovery. In our process, we use PDHFAC2 and ozone as the precursors, and the temperature was set at 200 degrees. And we finally got the PD thin film with high purities. And here is the XRD pattern and the SEM images of our PD thin films. So in conclusion, the fabrication using a PD precursor and an oxidation agent is actually feasible. Thanks for watching.